Let's now solve this frame structure. It is a symmetric structure, symmetrically loaded. We consider the uniform distributed load Q equal to 16 kilonewton meter. The cross sections of the structural elements are 65 by 30 cm for the horizontal beam, 40 by 30 cm for the lower columns, and 35 by 30 cm for the upper columns. So since it is a symmetric structure, we will consider only half of the structure in the cross method. We have to start finding the fixed end moment, as you know. So we will consider this scheme. We have node A, B, C, and L. So we have to consider the additional restraint here. This is of course a structure with nodes that can only rotate, so we lock the rotation. Here we have our symmetry axis. We consider the uniform distributed load on beam AB and on beam CL. They are both equal to Q. So the fixed end moments are these moments, of course. So we have that the fixed end moments corresponding to the first phase of the cross method in A is equal to minus, since it is counterclockwise, remember our sign convention that is positive moments clockwise. So M prime A is equal to Q LAB squared over 12, which is equal to minus 16 by 5 squared over 12. That is minus 33.33 kilonewton meter. Well, MB has the same value, but positive, since it is a clockwise bending moment. So we have MB prime is equal to 33.33 kilonewton meter. MC prime is equal to minus Q LCL squared over 12, which is equal to minus 16 by 7 squared over 12, equal to minus 65.33 kilonewton meter. Well, since we will consider a symmetric structure in the resolution with the cross method, we have also to calculate MJ prime, which is the value of the bending on the symmetry axis for a scheme of a beam clamp that both extremities subjected to a uniform distributed load, which is, as you know, equal to minus QLCL squared over 24. It is minus because by looking the node J on the left, we will have a counterclockwise bending moment. So it is equal to minus 32.67 kilonewton meter. Well, for the calculation of the distribution factors, we will consider the nodes one by one. So we start from node A, we are in this situation. So this is node A. This is the node B with the additional restraint locking the rotation. So when we remove the additional restraint in A and we give a unitary rotation, we will have this deformed shape here. This is node D and node G at the base. So remember that we have defined R equal to Ej over L, the rigidity of the beam. So E is the elastic modulus, and J, which is the moment of inertia, is equal to B h cubed over 12 for a rectangular cross-section having dimension B and H. Well, for the calculation of the distribution factors, we have to consider the rotational stiffness of the beams converging in node A, with, in this configuration, R 4RAB for beam AB, 4RAD for beam AD, and 3RAG. We now consider this table here for the calculation of the raw factors. We have the first column for the beams converging in the node. So we have beam AB, beam AD, and beam AG. The dimensions of the cross sections. In centimeters, so 30 by 65, 30 by 35, and 30 by 40. We calculate the moment of inertia J, which is in this measure, so centimeters to the power of 4. It is equal to 686,563 for beam AB, 107,188, and 160,000 for beam AG. These are the moments of inertia for the cross sections. The length of the beams in centimeters is 500 for beam AB, 400 for beam AD, and 500 again for beam AG. Well, for the calculation of the rotational stiffness, we have already observed that we do not consider the value of the elastic modulus, since it will be simplified in the calculation of the distribution factors. So, for beam AB, the rotational stiffness W is equal to 4J over L, and in particular, it is 5,492.5. For beam AD, it is 4J over L, and it is 1,071.9. For beam AG, the rotational stiffness is 3J over L, which is 960. We sum up the rotational stiffnesses. So we have the sum of WE, which is equal to 7,524.38. Then we can calculate the distribution factors, which are 0.73 for beam AB, 0.142 for beam AD, and 0.128 for beam AG. We have to check that the sum of the distribution factors for node B relative to node B is equal to 1, and this is respected in this case. We will now do the same thing for node B. We are in this configuration. So we have B, A, and C. In node A and C, we have the additional restraints locking the rotations. While in B, we remove the additional restraint permitting the rotation, so we have this deformed shape. The rotational stiffnesses for the beams converging in node B are 4RBC for beam BC, 4REB, 4RAB, and 3RBH. So using the same table seen before for node A, we have, well, we have beam AB, beam BC, beam BE, and BH. The dimensions in centimeters are 30 by 65, 30 by 65, 30 by 35 for the upper column, and 30 by 40 for the lower column. The moments of inertia are these ones. The lengths are 500 for beam AB, 500 centimeter. The same for beam BC, 400 centimeters for beam BE, and 500 centimeters for beam BH. Well, the W factors are these ones. So we can calculate the distribution factors, which are equal to 0.422, 0.422, 0.082, and 0.074. Considering that the sum of all the W factors is equal to 13,016.9, and the sum of the distribution factors is 1. So it is correct. We now consider node C. Here on node J we are on the symmetry axis. So we have this restraint. So the rotational stiffnesses are, if we assume the rotation, the unitary rotation in node C, are RCJ for beam CJ, RCI, 3RCI for beam CI, 4RBC, and 4RCF. So we have beam CB, beam CJ, beam CF, and beam CI. Here are the dimensions. The moments of inertia. The lengths. The W factors. Oh, sorry. The sum of all the W factors is equal to 9,486, and the distribution factors are 0.579 for beam CB, 0.207 for beam CJ, 0.113 for beam CF, and 0.101 for beam CI. Their sum is equal to 1. So this is the structure on which we will apply the cross method. We have written in the box the values of the distribution factors we have just calculated. Now we are going to write the first moments, so the fixed end moments we have found in the first phase, in which we have added the additional restraints and considered the distributed load on the beams. So these are the value of the fixed end moments, which are negative on node A, minus 33.33, positive on node B. The convention is always clockwise moments are positive. On node C we have minus 65.33, and on node J we have minus 32.67. Well, we have to start from the most unbalanced node, which in this case is node C. So we have to distribute the bending moment which is present on node C according to the distribution factors of the beams converging in node C. So we obtain these values of the second bending moments. They are of course positive, since they have opposite sign with respect to the first bending moments. Then we have to calculate also, considering the carryover factors, the third moments, which are these ones. Well, consider that for beam BC and CF, the carryover factors are 0.5 in both cases, while for beam Cj the carryover factor is equal to -1, and for beam Ci the carryover factor is 0, since on the support we will not have any bending moment. We have balanced node C. Then we move to node B, which is unbalanced because of the presence of a first bending equal to 33.33, and also because of the presence of the third moments coming from node C. So 18.92. We have to sum up these contributions and distribute the resultant according to the distribution factors. We will obtain these second bending moments. Then, considering the carryover factors, we will obtain these third bending moments. They have the same sign of the second bending moments. We move now to node A, which is unbalanced. Node B was balanced after the previous passage. So we move to node A, in which we have to sum up the two contributions, minus 33.33 and minus 11.03. And we have to distribute this sum according to the distribution factors, obtaining these second bending moments. Then we consider, also in this case, the third bending moments, considering the carryover factors, obtaining these values. Now, node A is balanced. Well, because of the presence of the third moments equal to 16.19, the node B is not balanced anymore. So we have to distribute this unbalanced bending moment, obtaining these second moments. Then we have these third bending moments. We have balanced node B. And we move now to node C, in which we have to sum up the contributions equal to minus 11.03 and minus 3.42, and then distribute the sum according to the distribution factors, obtaining these values for the second bending moments. Then we have to calculate the third bending moments, which are these ones. And now node C is balanced. We now consider the unbalanced bending moment in node A equal to minus 3.42. We distribute it, obtaining these second bending moments. Also in this case we have to consider the third bending moments. And now node A is balanced. We now consider node B, in which is present an unbalanced bending moment equal to 1.25 plus 4.18. So we distribute this bending, obtaining these second bending moments. We write also the third bending moments. Well, actually, since these values of the third bending moments just found, and in particular the values minus 1.15 is a low value, we will stop here. So, as you know, we stop in the cross method when we obtain an unbalanced bending moment which is sufficiently small. So we will now neglect this last contribution, so we will neglect this value here, so the minus 1.15. Well, we have now to sum up all the contributions found and then check the equilibrium at the nodes. If the equilibrium is not respected, then we have to continue our iterations. So, we will write now the values of the resultant of the bending moments in each node. Well, in the red box are presented the resultant bending moments. If we now want to check the equilibrium at the nodes, we can sum up all the bending moments in node A, and we obtain an error of 0.01. Then we can do the same thing for node B, and we have 0, so it is perfectly balanced. For node C, we have minus 0.02. So we have sufficiently small error, so we have that the equilibrium is respected. And this is the final scheme for the cross method. Well, according to the values we have found by solving the structure using the cross method, we are able to draw the bending moment diagram, which is this one, considering the symmetry of the structure. Well, in order to determine also the shear diagram, we can start from the values of the bending moments already obtained, and we can consider these situations for each beam. So we start from beam AB. We can consider the beam as a simply supported beam subjected to a uniform distributed load, which is the load acting on beam AB, and Q is 16 kilonewton meter. And then we have also to consider that we have the two bending moments coming from the resolution of the structure with the cross method, which are 12.9 on the left and 19.6 on the right. So we can consider the shear on this beam as the sum of two contributions. One, which is the contribution due to the uniform distributed load. So it is equal to QL over 2. And then we have a second contribution given by the presence of the two bending moments at the extremities, whose diagram can be considered linear. So in this case, we have these two contributions. That will be calculated in a minute. So the length of beam AB is equal to 5 meters. This is extreme A and this is the extreme B. Well, if we want to calculate the shear in A, BA, we have to sum up the first and the second contributions. So we have QL over 2, which is the first one. Then we have minus, since they have opposite sign, MA plus MB over L. MA is 12.9, so it is this bending moment here, and MB is 19.6. In this formula, we will take the moments with their sign. So we can write 16 by 5 over 2 minus, well, the bending moment MA, according to our sign convention, is negative, so minus 12.9 plus MB, 19.6 over 5, which is the length of beam AB. By solving this expression, we obtain a shear force equal to 38.7 kilonewton. The same thing we can do also for the shear in B. So we have QL over 2 plus, since in this case the two contributions have the same sign, MA plus MB over L. So 16 by 5 over 2 plus minus 12.9 plus 19.6 over 5, which gives a shear equal to 41.32 kilonewton. While considering the linearity of the shear diagram, we can evaluate also the points in which the shear is 0, which corresponds to the points in which we will have the maximum positive bending moment. So, by a simple proportion, we can evaluate xm, the abscissa along the beam on which the shear is 0, as VA over VA plus VB by L, which is equal to 2.42 meters. And then by knowing this position, we can also calculate M max, which is equal to VA, the shear in A, by xm, minus Q xm squared over 2, minus MA, equal to it is equal to 38.7 by 2.42 minus 16, which multiplies xm squared over 2, minus MA, which is 12.9. This is equal to 33.9 kilonewton meter. This is the maximum bending moments which tense the intradox fibers. Well, we can do the same for beam BC. So we consider, as before, the beam BC simply supported. We do not have any uniform distributed load, so we will consider only the bending moments MB and MC found with the cross method at the extremities. Well, and in particular, we have MB, which is equal to 8.07 kilonewton meters, and MC equal to 31.75 kilonewton meter. The length of beam BC is 5 meters. So now we have only the contributions due to the presence of the bending moments. So we have VB and VC that are equal. So in particular, VB is equal to minus MB plus MC taken with their sign over L, which is equal to minus 8.07 plus 31.75 over 5, which gives minus 4.74 kilonewton. And Vc is equal to Vb. In this case, indeed, we have a linear bending moment acting on beam BC, so we will have a constant shear diagram on this beam. Well, in order to determine the sign of the shear, we are considering this convention here of the elementary portion of a beam. So this is the positive convention for the shear. Well, for beam CL, we have this situation. We have the uniform distributed load Q acting on the beam. And then we have also the two bending moments at the extremities, ML and MC. Well, here passes the symmetry axis of our structure. So we have that the two bending moments, MC and ML, are equal and are 48.18 kilonewton meters. The length of beam CL is 7 meters. So here, the shear is given only by the first contribution due to the uniform distributed load. So we will have these two components for the shear, QL over 2. Well, so VC is equal to VL and equal to QL over 2, which, substituting the values, is equal to 16 by 7 over 2, which gives 56 kilonewton. Well, for this beam, for sake of symmetry, we have that the point in which the shear goes to 0 is on the symmetry axis. That is the point in which we have the maximum bending moment, which tends the fibers at the introducts. And this value of the bending moment is the one we have already calculated on the symmetry axis with the cross method, and in particular it was equal to 49.18 kilonewton meters. Well, in the columns, where we have linear bending moment diagrams, the shear can be calculated simply in this way. So let's consider beam AD. We have two bending moments applied at the extremities. So it is 3.39 and 6.79. Well, the shear force is simply the sum of these two bending moments divided by the length of the column, which gives two forces acting in this way, and they are both equal to 2.55. Since we know that when we have a linear bending moment diagram on a beam, we will have a constant shear diagram. So let's now consider the column AG. We have a bending moment here on A equal to 6.12 and a zero bending moment in G where we have the support. So in this case we have simply to divide 6.12 by the length of the column, which is 5 meters, obtaining these two shear forces, 1.22 and 1.22. While the length of the column AD was 4 meters. Well, we can do the same thing for the other columns. So let's consider column BE with these bending moments. The shear forces are these ones. Then we have beam BH. And zero bending moment in H, where we have the support. In this case, we have the shear forces, which are equal to 1.1. And finally, for column FC, we have 4.51 at the top and 9.01 on C, which give shear forces equal to 3.4. And CE, we will have a bending moment only on C equal to 8.04. And shear forces equal to 1.61. Well, these shear forces, as you have noticed, are basically determined by equilibrium. Well, the sign convention for the shear is this one. If these are an elementary portion of the beam, these are shear forces taken to be positive. So we are now able to draw the shear diagram, which is this one. Well, we have now considered the flexural behavior of a beam. Let's assume now to have a frame like this. While in the resolution of the cross method we have just seen, we have, for example, calculated the flexural behavior of a beam of this frame. If we now want to look at the axial force on the column, we can isolate the column and apply the cross method. So let's assume to isolate the first column here. So I have to apply the cross method in this configuration, considering, of course, all the loads that are acting on the beams. Then, knowing the shear diagram, we can determine the axial force on the column by equilibrium at the nodes. So we will obtain, if this is the column, let's say on the beam at the top, we can obtain this shear diagram as an example. Oh, sorry. and also on the second beam. So this is beam B1, this is beam B2. Well, if we now isolate the nodes, we have that from the right we have TB1, which is the shear force for the beam B1 calculated with the cross method. Then, in order to determine the axial force on the column, we do it by considering the equilibrium, and we found N1 on the column, which is a compressive force. This is node 1, let's say. If we now consider node 2, we are in this situation. We have the force N1 coming from the column 1. Then we have the shear force TB2, which is the shear on beam B2. We sum up these two contributions and we obtain a compressive force N2 on the second column. So basically we can write and we can determine the axial forces on the column by equilibrium. N1 we have seen is equal to TB1 and N2 is equal to TB1, that is N1, plus TB2. So this is the way in which we can find the axial force on the column.